Next presentation is from Dr. Matthias Steiner at INCAR-RAL. We'll be talking about urban environment weather challenges.
You know, Stephanie set the tone nicely, the stage for what is happening from the operational side with the HAMS tool. And she clearly hinted that I will be talking a little more out in the future. So what you will hear from me in my presentation is really more what's happening on the research side. That is still significant ways away from being accessible in operational environments, but it gives you a flavor of the kinds of things that we can do nowadays. Next. Actually, make another next here. So whether what you see here, and I don't want to go in detail, it really affects operations, as we know, on the ground, in the air. It's the safety aspects, the efficiency that plays into it, and the reliability, ultimately. And so it's all the known weather elements, whether it's thunderstorms, extreme temperatures, wind, precipitation, all that is playing a role also for these emerging modes of transportation that Stephanie already hinted at, like advanced air mobility, as NASA calls it these days, which includes unmanned aerial systems and urban air mobility. And here I want to really focusing in on the urban side of things in this presentation, which will, as you will see, will pose some additional challenges that we are not familiar with, at least from an aerial perspective. Maybe some of you who have flown in urban environments will appreciate what I'm talking about here. So next. And as the aircrafts get smaller, obviously they become more sensitive to weather impacts. And when you look at some of these emerging designs of these electric vertical takeoff and landing aircraft, they still have to figure out what the performance characteristics are and how they're gonna deal with wind and turbulence, particularly in complex environments. So far, what I've seen mostly, they are concerned in trying to get the aircraft off the ground and get initial flights going, but I don't know how far they have examined the weather aspects of things, and it's difficult to get that information out of them, what the performance characteristics are, such that we understand what the thresholds, the critical thresholds would be that we would have to predict for in order to provide. So there's still a lot of work to be done. Next. Particularly challenging environments are complex terrain, thunderstorms, urban landscape, or if you are near significant land surface contrast, land water bodies, or fronts. What you're looking at there is a haboob, but it's a nice picture. It shows you actually the frontal line as it moves over an urban location there. Next, please. When you think in these particular challenging environments, you really have to understand that there is a wide range of atmospheric processes and scales going on. And we have pretty much limited weather guidance for these low-level operations, particularly in those challenging situations. And that is kind of what the next slide is highlighting. And again, next, Rex, please. And you can click one more time here. This is, you know, a lot of information on this slide, but just look at the smiley faces there and the different colors. We did a significant assessment for NASA in terms of what weather information is out there to support aviation and at various scales. And as you go in this table from the middle to the right, it goes from synoptic to mesoscale to storm scale and then urban scale. And as you really get into these local scales, you see how these smileys turn from green to more yellow to red. And all the way on the right in the urban environment, really that fine scale guidance there's a significant gap there, that there is not that much information available to provide guidance for those kind of emerging operations. Next, please. And one more time. So from here on, I really want to focus primarily on winds, and there's a variety of processes and winds. There's clearly the thermodynamic circulations that you see sketched there, which the driving force behind it is really the differential heating that you see throughout the day, you know, land water contrast or mountain and valleys, and you understand these circulations, or you can explain these circulations primarily through thermodynamic heating differences throughout the day. Next. Another significant source of wind is if you have strong pressure gradients, like you see along frontal boundaries, or strong downslope windstorms that you see there in the California area with the Santa Ana winds or the Diablo winds in that area. That can be pretty strong. We also see it here in Colorado, where I'm residing, particularly in this time of year. Next. Or thunderstorms. Thunderstorms have their own local circulations. There are strong or potentially strong outflows and gusts, tornadoes, and so they are potentially very hazardous to aviation, as we know from the large transport aviation, these accidents in the 70s, 80s, and 90s that were related to wind shear problems. They were really caused by thunderstorms or terrain under certain circumstances, and are very hazardous. Next. And as you zoom one more into the urban landscape, there's a lot of things going on related to channeling of the air in the urban street canyons, or you get vortex shedding off the buildings that creates quite a bit of turbulence. And I want to really zoom in this talk later on those kinds of aspects. But first, let's highlight some of these examples on how they manifest themselves if you look at wind climatologies. And since we talked here about California, if you go to the next slide, this is looking at Los Angeles, sort of the regional domain in terms of where urban air mobility may be operating from downtown LA or from the LA airport, and you may fly through the region, you know, 50-mile radius is shown there, maybe a little further than that. And so you see a variety of locations that may be downtown with high rises, the airport near the ocean, or residential areas with smaller buildings, etc. Next, please. So if you look at the regional wind variation, what you see here, these are all wind roses from different locations throughout that domain, collected by ASOS or AWOS stations. And the wind roses are shown for every month. So if you really look closely, you see there is from January through December, every month, the wind rose, and an example is shown in the upper right that is essentially giving you a climatology of the predominant wind direction and wind speeds. And so you see that there is notable variation in the wind speed and direction throughout this domain. So if you only had one station at Los Angeles Airport, it would not be representative for what's going on throughout the domain. Next, please. This is maybe more easily understood looking at this graphic, where in each plot that you see there, from the top down is the seasonal cycle from January through December, and the horizontal axis is the diurnal cycle in UTC from 0 to 23 UTC. And what you see color-coded is the frequency of wind speeds exceeding 10 knots. And obviously you can do that for any wind speed This is just as an example for 10 knots. And what you clearly see that at some location like LAX, the airport in Los Angeles, you clearly have winds in the afternoon that exceed 10 knots very frequently throughout most of the year, maybe less so in the cool season, but most of the year you see that pretty yellow-red blurb there that shows that. And you see that in several places throughout the area, also up in Lancaster in the north, or in Chino to the east, but it's not the same everywhere. If you go to the next slide, this was sustained winds. This is now the gust frequency, and you see that particularly up in the more mountainous area, Lancaster, that there the gusts are very frequently associated with those higher winds. But that's not necessarily true in all of the other locations. Next, please. So now let's zoom in into urban environments and really go from the regional to the very small local scale. And as you see in this picture already, there is a lot of high rises there. And so the question is, how can you understand what's going on in there? How would you be able to model that such that you could provide forecasts? And so this is just a background slide here that I have shown. You can click one more time, Rex. I think a couple of years ago when I was talking about this for the first time. This is just a different scales from the left, going from the large weather system scale through thunderstorm scale, more in the 10 to 1 kilometer range, and down to building scales and street scales all the way to the right. When you look at the current models that we have in the US, for example, we have the global weather prediction models. They have sort of a grid resolution on the order of 20, 30 kilometers. And then you go more to the mesoscale model, like the RAP that Stephanie mentioned, and the HRRR, the high resolution rapid refresh. They have grid resolutions on the order of 10 kilometers, or then on the order of 1, the HRRR specifically is 3 kilometers. And but that's not good enough to really resolve what's happening in an urban street canyon that is maybe 30 or 100 meter wide. So you need to get into much finer resolved modeling capabilities. And that's what I show there on the right with the microscale research models, dwarf LES large eddy simulations, where you can get at the sub-kilometer scale, or fast eddy that I will be talking in a moment some more. This is a very unique model that we are developing at NCAR, where you can go down to really meter scale, literally. One more click, please, here on this. The problem here with the resolution is that how many grid points do you truly need in order to resolve processes at a particular scale? So if you have a model that runs at 3 kilometer grid spacing, that doesn't mean that you're actually resolving processes at that grid resolution. And so you can think in terms of, imagine a sinus wave, and how many samples do you have to take on that sinus wave to recognize that it's a sinus wave? And so you need on the order of 5 to 10 samples to start recognizing the pattern underneath, which means if you want to resolve an urban street scale, 30 to maybe 100 meter width, you need to really be able to model the processes down to meter scales. And then the challenge comes on top in terms of observations. Do you have observation to actually validate these kinds of predictions, etc.? So next, please. So this is just a higher level graphic on the fast eddy model, how we go about doing microscale weather modeling. And the trick behind this is that we have a completely rewritten weather prediction model code to fully reside in the GPU, the graphical processing unit environments to make full use of the acceleration that you can get from that. And you can achieve probably up to 2 orders of magnitude faster processing, which means you can start with, running models at much higher grid resolution and start resolving these microscale processes. In the graphic in the upper right, you just see a comparison of the processing speed. The lower curve there is for traditional CPU processing, and the more rapidly increasing curve shows you what you can achieve with graphical processing units. And that's really what we are after. And so we have rewritten a numerical weather prediction model to fully reside in GPU. We have done the full dry dynamics formulation, and it's fully tested. So we can really get at the microscale turbulence. And we embedded explicit representation of building effects in the model such that we can run downtown areas in urban environments. We're working on the moist dynamics. That is on the way. I have seen initial simulation results that look realistic, but they still await validation. Speaking of validation, for the dry situation, we have done extensive validation on various cases like canonical, neutral, convective, and stable boundary layer regimes, flow over terrain to understand the flow over or around smaller mountains. We have looked at wind tunnel laboratory experiments down to millimeter scale, where you look at small buildings with 2 centimeter side lengths set up in wind tunnels, and we ran fast eddy at 1 millimeter resolution in order to reproduce what the measurements in the wind tunnel were able to were showing, and we can really reproduce those things very nicely. We have also looked at real field experiments from urban environments, like the joint joint experiment in 2003 in Oklahoma City. That was from a defense perspective. They were interested in pollution dispersion of potentially toxic agents, and so they put in additional wind sensors and other things. And again, even in a natural laboratory like that, we have been able to very nicely reproduce what the observations show within the uncertainty of the observations and the comparisons, obviously. Those 2 papers shown there on the bottom right are papers that are published in the American Geophysical Union James journal, and they are open source. These articles, you can look them up. They fully describe the model in the one paper and the extensive validation in the other one. This is just background information to say what I will show you now in the next few slides. We have worked hard trying to validate. It's not just looking nicely, it is probably doing a pretty good job at simulating things. So now I want to shift gear from California more over to Texas and focus on Dallas, and particularly the Dallas downtown area as to what's going on there. You see a wind climatology in the upper right, the wind roses, the seasonal variation, January, April, July, October as samples, highlighting that in that area at the Dallas-Fort Worth, by the way, this is the climatology from that ASOS station, shows largely a southerly component throughout the year with a northerly component that is significant through the cooler season. But there is significant seasonal and diurnal variability. And when you look at the plots on the lower half on the right, the upper one shows the likelihood of wind speeds to exceed 10 knots. These are the same graphics that I've shown you before for the LA region. And so again, it's from the top down, January through December in the vertical axis, the seasonality, and left to right is the diurnal cycle. Again, you see there is significant maximum wind speeds in the afternoons associated with wind gusts, and that's particularly significant in the spring season there, maybe less so in the summer. So the next slide is starting to show you simulations from FastEddy. Oh, well, yeah, it's fine, leave it. This is showing you in the left graphic the top two, well, let's go in the columns first on the postage stamp graphic on the left. You see January, April, July, October, and in the rows is early morning, like 6 local time in the top row across, and the second row is noon, mid-afternoon, like 3 o'clock local time for wind speed in the upper two, and then turbulence kinetic energy in the lower two rows. So these are just for some sample days out of these particular months, and you see significant variability from different seasons. You also see that during the day the wind speeds increase, which you see particularly there in the April afternoon postage stamp graphic there, with southerly winds that are significant on the order of 10 knots or so, 10 meters per second, which is more than 10 knots. And if you look closely, you see the downtown buildings there and the turbulence generated by that, particularly in the lowest April in the bottom part there. You see where it gets really red and yellow. That's where you see significant turbulence. And if you look at the bottom right graphic there, those postage stamps, this is just from a January situation where we took midday, noonish time, and for each day of January, you see the variation of the wind direction and speed. And this is just giving you an idea of how varied from day to day and even within the day that the wind speeds can be in the urban environment. And I should have said this before, this is really zoomed in. Each of these postage stamp graphics is on the order of 3 or 4 kilometer side length. So that's roughly the resolution of the high resolution rapid refresh that is currently run operational in the US. So all this, what I'm talking about here, is completely subgrid scale. And you start resolving those wakes that the buildings are generating, and they can pose significant turbulence hazards. And depending on the situation, the wind direction, the wind speed, and the daytime heating, these turbulent areas may extend well above and downwind of the buildings. And so if you go to the next slide, Rex, I want to show you an example. Oh yeah, it's running great. This is a cold front passage through the Dallas downtown area. Oops, did it stop? Okay, good, great, thank you. That was on 11 November in 2019. And you see there in red the outline of what the HRRR pixel would be about it, in terms of size and what FastEddy may resolve. And so the wind speeds come from the southwest initially, the direction, and then turn away or all the way around, eventually come from a northerly direction. And what you're looking at in the left graphic there is vertical motions, up and down drafts. Red is updrafts and blue is downdrafts. And on the right panel, you see wind speed. And this horizontal cross section is taken about 26 meters or so above ground level. So it's relatively low within the urban canopy, what you see there. And you can clearly see the very dynamic nature with a lot of up and down drafts, very granular, and the wind speed. You see vortices being generated, etc. The bottom graphic is showing you essentially the time series taken at 3 locations that are indicated in the upper plots. And with color coding, the top row shows you the wind speeds The second one is the wind direction. The third one, turbulence kinetic energy, essentially how turbulent the environment is. And the bottom one, the temperature. And you clearly see as the front passes through after 16 UTC, within an hour or less so, the temperature significantly drops and the wind speeds increase, the direction changes, and the turbulence is significantly enhanced. But it depends on which location you are in terms of what you're seeing. Next, please. So thinking in terms of going back to observations, when you look at the observing network, what's shown in the upper right graphic is in the horizontal axis is the spatial scales, and in the vertical axis is the temporal scales. And you see highlighted in those blue area different kinds of weather phenomena and the scales from synoptic in the upper right going down to mesoscale and then the microscale in the bottom left. And you see different observing infrastructures, what the satellite and the radar and the ASOS network can cover, but it really is not good enough to give you coverage of the microscales in the lower right of lower left of that graphic. The kinds of things I was showing you before with how dynamic a downtown area and urban environment can be. And so then the question comes also, not just what is available in terms of observations, but also where do you place those sensors? And typically the guidance is that, oh, you want to have it unobstructed in an open space like you would put at an airport like Dallas-Fort Worth, where you place the ASOS such that it gives you a representative reading of what is going on. But when you start getting into an built-up environment, and the bottom right shows you a single building, a horizontal top-down view, and then a cross-section in the lower half of how the flow of air is going around and over the building. And you see that there is a lot of vortices that are being generated by the building. And so if you start thinking of where do you place your sensor, how representative may that reading be, it's pretty challenging, and you may have to mount those sensors very much above the building itself to get out of these vortices. On the other hand, if you were to think of landing on the rooftop of a building, which is some of the ideas that urban air mobility is envisioning, then you will actually have to understand these vortices because you have to fly through them in order to land on the rooftop. So this is not straightforward. Next, please. Next slide. Yeah, thanks. So we looked at the Dallas area, the downtown area. What is there already in terms of current infrastructure, existing heliports? And you see there with the red circles, 3 locations that are near the convention center, and then 1 rooftop, the 9TA4 landing spot on the top of the Santander Tower building. Some of them are public, some of them are private landing spots, but these are existing heliports in the Dallas downtown area. And then in the right, you see the Baylor University Medical Center has one too, but that was just outside our modeling domain, so we didn't look at that more specifically. But we also added some additional vertiports that we felt like, oh, these could be potentially future landing spots because of urban air mobility wanting to utilize existing infrastructure like, large parking structures with a flat rooftop or so that they might look at. And how does the situation look there? So we tried to bracket things in that environment from open space landing spots to rooftop with taller buildings around, to rooftop of the very tallest building, to understand what is the air doing around these landing spots, how dynamic is it, and how can we visualize that? Rex could talk a lot about this in terms of the helicopter operations and others too, obviously, that are on the call, how you're trying to land into the wind rather than with a tailwind and the wind and turbulence around the buildings. And that obviously depends on the type of aircraft you're flying. It depends on how experienced you are as a pilot as to what those critical thresholds may be. Bottom right, that graphic is just a snapshot of the 2020 flight operations in the Dallas downtown area. And you see that the landing spot 49T at the southwest corner of the convention center is really a popular landing spot. But I think this may be the only one that is public there among those. Next, please. So we looked at the turbulence near landing spots. And so I created these postage stamps that you see in the upper right, where in the center panel, we look at a horizontal cross section of the turbulence kinetic energy. How dynamic is the air? And that this is only a 300 by 300 meter domain centered on the landing spot. And you clearly see there with the more hot colors, yellow and red pinkish, where the most intense turbulence is in that domain, just about 10 meters above the landing spot. And then the surrounding postage stamps are vertical cross sections. And in each of those panels, as you go color coded from more reddish to bluish colors, it goes further out in radial direction, looking at a vertical profile above the landing spot in terms of what the turbulence kinetic energy is. And so you can visualize in a three-dimensional sense of how this looks like for each landing spot that you may envision, whether they exist or potentially in the future, if you want to examine whether a location is good or not for something like that. We also thought in terms of, how to complement observing infrastructure in an environment like that. And clearly mounting sensors on the rooftop somewhere is only giving you a very local specific reading, and it may not be representative for the larger environment, well, larger in a relative local sense. And so you may have to start looking at things like LiDAR scanning, iSafe scanning LiDAR infrastructure, where you maybe mount them on rooftops such that you can scan what is going on. And the bottom center graphic is actually an example from the Washington, D.C. area, an NCAR LiDAR that was ran for an experiment there a few years ago. And scanning, here you see a gust front coming in, and you can map that front as it progresses over the urban landscape. You can also think in terms of equipping the aerial vehicles themselves with sensors, in situ weather sensors like we see on the large transport aviation. The sensors are getting so small that this is no longer an issue of putting MET sensors on an aircraft, even as small as a drone. But you can also think in terms of LiDAR observations on board of the aircraft. It would not only help in terms of detecting a void of hazards like buildings, but potentially also alert you of upcoming very dynamic turbulent areas ahead of you. And then you can put that information together and create situational awareness, etc. So there is many opportunities there that the industry should start thinking of making use of. Next slide. This is just some more examples related to what's happening around the vertiports. We also looked at in the bottom half in terms of what would you experience along a flight path coming in onto that landing spot. What do you experience along the flight path, and how would that compare what a reading will give you at the location? And this comparison, it's all based on the fine scale model simulations, obviously, just reading out values. But it's clear that what you see or would see from an observation at the landing spot, like an ASOS at a rooftop landing spot, is not giving you representative information to what an aircraft flying into that landing spot would be experiencing. You clearly need more than that. I also know that the time has been running, and Rex, you should have been stopping me, so maybe let's just skip through a couple of slides. Yeah, go through that one. This is essentially how you would translate things. Go to the next one. Click one more time and click another time there to just make, yes, exactly. So this is kind of just an outlook in terms of what needs to be done from an R&D perspective. Clearly, we need to better understand the weather hazards. And what I've been showing you with how dynamic urban environments are, we're only starting to grasp this from a scientific perspective and from how to be able to simulate that and ultimately create forecasts. But we also need to understand what the performance characteristics are of these vehicles that will be operating in these environments in order to understand what constitutes a hazardous situation for these aircrafts. Observing infrastructure, I elaborated on that. There is a lot of opportunities to sample more of the atmosphere in these environments through various means, either ground-based, in situ, or remote sensing, and also putting sensors on the aerial vehicles themselves. Next slide, and click through 3 more times, I think. Yeah, that's good. And then you can start thinking in terms of weather guidance. What are you actually providing to an operator in order to enable operations to be safe, efficient, and reliable ultimately down the road? We need test beds. Stephanie was talking about the Aviation Weather Center test bed. That's one thing, but I think we need real test beds out in nature to be able to demonstrate and learn how to crawl, walk, and run in these environments with vehicles that we may not yet fully understand what their performance characteristics are, decision support tools, and ultimately what are the requirements in terms of minimal weather guidance that needs to be provided in order to enable safe operations. I mean, operations are happening off airports, low level already, but this is based on the judgment of the operator, and maybe we need more than that. So I think I stop at this. Thank you.
Well, thank you, Dr. Matthias Steiner. Greatly appreciate all that information. That is a significant amount. We'll open it up to questions. I have one question, and I'm going to ask I saw that you put a couple questions in the chat, which is great. I'm going to have you unmute and ask your question directly to Dr. Steiner. So Jim Cooley, I believe that's how you pronounce your name. Jim, if you want to unmute and ask your question to Dr. Steiner.
Yeah, that one animation model, I believe it was of Houston on that November 2019 day, was just incredible. So let me give you the accolades there first and foremost. That was just awesome. And so I was curious though, how is turbulent kinetic energy measured or calculated? And apologies if you actually said that already.
Turbulence kinetic energy is a metric that is generated by the model itself. It's a measure of how much variance is in the flow itself. And so I don't actually know in particular explicit, the equations at how that is equated. And it's not the same as the eddy dissipation rate as the ICAO standard for turbulence that is used for large transport aviation. We can, through post-processing, we can create eddy dissipation rates, the EDR, as well, instead of the TK, the turbulence kinetic energy. But it's still unclear how that actually would be utilized for these very smaller aircraft is that still a meaningful metric or not? So it's just one metric, turbulence kinetic energy, that the benefit is it's coming out of the model straightforward. So that's why it's convenient to look at that. But is this the ultimate variable that the industry needs in order to guide operations? That remains to be seen.
All right. And our second question comes from John Stevenson from the FAA. John, are you able to unmute and be online? I'll let you ask your question directly.
I'm sorry I missed half your brief, Matthias, but I did already mention this in the beginning. I apologize. But a few years ago, we were approached by Dr. Melton from NASA for a letter of support. Not any funding, but just that they supported this research that they were doing into machine learning for urban wind estimation. And I just want to know if you're familiar with his research and his study on that. And if not, I could help you get connected with him and what his research has developed. I haven't spoken to him in at least 18 months or more. So just wanted to bring that up if you weren't aware of his research.
Yes, I'm very much aware of that. They are trying to use data mining and machine learning approaches, trying to emulate what a model like what I was showing would try to do. And to a certain degree, you can do that, but you still need to understand what are you training the model on in order to get that going. So you would have to create a database of simulations to capture the range of weather conditions. And so what he was doing, I think, is using more of computational fluid dynamics approaches, which are simplified. They don't have real weather conditions in it. We drive our model with real initial conditions that we get from the atmosphere. So there is more to it than just wind speed and direction. There's the whole profile. There's the atmospheric stability from the temperature profiles, etc., and how that varies over time. So once you start trying to capture all those various conditions, you really expand your lookup table, so to speak, or your database that you're trying to harvest through these data mining approaches, which means you still have to do the simulations one way or another in order to give you some background on how to train your machine learning approaches to reflect the dynamic nature in the environment. I could certainly see down the road some combination of things that include observations, whether it's in situ remote, that includes some sort of fine scale simulations and maybe data mining approaches in order to provide guidance to operators. But that's way down the road, and we'll have to see what makes most sense from a processing perspective also, because these fine scale simulations, you're creating a lot of points. I mean, you're getting into millions of grid points, even just on a subgrid scale, small domain, like I shown for Dallas, Fort Worth. I mean, this cold front passage, I only have 3 hour simulation there. This is probably on the order of 100 million grid points, just to give you a magnitude of how much data we're talking about.
All right, thanks, Matthias, appreciate it.
All right, and I've got another question came in from our very own Tom Judge, more of a statement than a question. Tom, you want to address this with Dr. Steiner?
Sure. Thanks, Dr. Steiner, for this really thorough presentation. And apologies for the thumb typing, but one of the constant challenges that helicopter operators, and this will extend through to other operators in the future, is the neighbor relations around, especially urban helipads and raised helipads, and I think there's an imperfect way. I mean, we did, the designers did extensive wind tunnel testing on a new pad safety of the pad and kind of what's going for landing, the actual landing and departure to make sure it's safe. But then what we end up realizing is that significant amounts of time, due to other wind and temperature considerations, the pilots have to deviate from sort of the agreed approaches and departure paths, which we have 3 into that helipad, but probably 15% of the time there's a deviation. And the deviations virtually always result in 1 or more noise complaints. So, the FAA is, challenged with managing neighbor relationships over airspace. And I think there's a lot of work here that can help people better think or even better prepare people to understand that no approach and departure path agreement is going to be perfect in every circumstance. So thanks for this great, and apologies for the thumb typing.
Absolutely. And as you said, you have to adapt based on the current conditions in terms of how you approach a landing spot such that you can, land into the wind rather than with a tailwind, etc. And that will affect obviously where the noise is going. Along those lines, we're actually looking at adding a noise prediction capability to these fine scale modeling outputs, such that we could look at or start looking at how would the noise propagate in a given situation, location, given weather situation, to start highlighting some of those issues and visualizing them.